Thank you, Don. I'm glad everyone is here today and still hanging around on day 5. Yes, everyone's caffeinated. Well, Katie's caffeinated. I would like to share with you today a mission concept called MIRECLE. This stands for Mid-Infrared Exoplanet Climate Explorer. And I am shocked to tell you that I think this is the first time the exoplanet missions slide has actually shown up in the entire week of our conference. This used to be a staple. This was like every presentation like 3 years ago, everyone would pull up the slide and talk about it. Nonetheless, here it is. So you can appreciate it. And what I want to bring up is put MIRECLE in the context of all of the other exoplanet missions, specifically relating to exoplanet characterization. And now the first 2 decades of exoplanet characterization, we had the Hubble and Spitzer space telescopes. These were amazing facilities that were not necessarily designed for atmospheric characterization. Nonetheless, they achieved excellent, amazing precision and results. And Nicole went through a lot of those in her presentation earlier today, so I will not repeat myself on that. There's this telescope called James Webb Space Telescope. Has anyone heard about it? It's pretty cool. I check it out. There's some good stuff going on. No, so it's going to be studying a lot of rocky M-dwarf planets in its lifetime, trying to answer questions like, do these planets have atmospheres? What are their temperatures at their surface? Could you potentially have liquid water at those surfaces? But it'll be hard pressed to answer the question of habitability. Doesn't mean we won't try for 20 years, but it's going to be a challenge nonetheless. Part of the reason why for that is that just the sheer number of transit observations that you need to acquire to detect biosignatures. An example would be the TRAPPIST-1e system, where you need something like 85 transits, which doesn't sound like a lot when you know the orbital period's about 7 days, but you can only get about 10 or 11 transits a year. So it takes a long time just from a visibility window standpoint to actually build up those transits. Fortunately, we have Habitable Worlds Observatory, or HWO. Whoa. That goes back to Blossom from the 80s. Sorry, people. Yes, it'll be looking for Earth-like planets around sun-like stars, and that's very exciting. But there's also this sort of gap in between the JHU and Habitable Worlds, where I think there is an opportunity to characterize the nearest non-transiting habitable zone planets to understand habitability. So I'm going to be talking about those planets that are, within 20 parsecs of here. And shout out to Ted Johnson. Thank you very much for creating this plot. Here I'm showing you stellar insolation. So that is, Earth at 1. Hotter planets are higher up, cooler planets are lower down, as a function of distance from the Earth. And what you'll notice is that the 28 nearest known exoplanets are non-transiting. Those are planets that we can't currently study their atmospheres, right? Because methods today rely on transits. At some point, we'll have direct imaging. We might be able to study some of these planets' atmospheres, but they're around M dwarfs, right? They're close in short orbital periods. Maybe some ELTs might be able to study some of their atmospheres, but in terms of biosignatures and habitability, that isn't really on the table. You'll see I called out the TRAPPIST-1 system there and LTT 1445. So, this is a missed opportunity that I hope we can change. So before I go into the MIRECLE concept itself, let's talk a little bit about the method in which we'll be studying these atmospheres. So astronomers like to study the universe along 3 primary axes. And the first of which is space. So a prime example of that is direct imaging, right? You can spatially resolve the planet from the star and understand its atmospheric composition and characteristics and so on and so forth. That is a great way to study planets. There is another axis, time. And a perfect example, of course, is transiting exoplanets. We can temporally resolve these planets by looking at a system and staring at it and measuring the dip in light as a function of time and say, yes, we've detected a planet that's transiting. But there's a third axis. What's that third axis? Wavelength. right? Of course, yes. We always like spectroscopy. We study planets as a function of wavelength. And so back in 2020, I proposed a new way of studying exoplanet atmospheres that requires broad wavelength coverage that allows you to spectroscopically resolve the planet from the star. So how does this work exactly? It's called planetary infrared excess, or PI technique. And the basic concept is that you have okay, we'll take the SED spectrum figure on the right here. This is flux as a function of wavelength. And I'm showing you two black body curves. The blue is for a star, and then the orange is the star plus the planet, but I've magnified it by a factor of 1,000 for the planetary mission, just so you can see what's going on. So how does this work? Well, there is a wavelength range at which there is no thermal emission, where you only have contribution from the star. So that's the reference wavelength range over here that I'm showing. If you were to fit a black body model to this wavelength range, you would get a good constraint on the stellar spectrum, and you could extrapolate it to longer wavelengths, and you would see that it doesn't quite actually match up with the data because there's some infrared excess, some signal that is contributing above and beyond that of the star. And so if we attribute that to the planet itself, we can then do some simultaneous measurements and infer the properties of both the star and the planet simultaneously. This works very similar to how they look for circumstellar disks, or if you're looking for binary companions, you could do a 2SED model fit for that. Conceptually, it's the same. It's just that the signal sizes are significantly smaller. If you want more information on that, there's the first 4 papers in our series right there. I'll be touching on some of the topics throughout that this talk. Okay, so what I showed you before was for 1,000 Kelvin planet, but what about a potentially habitable planet? Let's look at how the signal sizes are for Proxen b. This is the nearest planet in our system, and if you look at the shortest wavelengths, right below 5 microns, it's 10 orders of magnitude difference in signal between the star in orange and the planet in blue. So yes, it is effectively, you're just measuring the stellar flux at these short, 1, 2, 3, 4, 5 microns. But at longer wavelengths, mid-infrared wavelengths, the contrast ratio isn't so bad. It's only 4 orders of magnitude, which in astrophysical sense is not bad, right? And you can see the flux in gray there, the planet-to-star flux ratio. You're looking at 50, maybe 80 part per million signal from the planet. That's doable. I mean, JWST is reaching that level of precision right now. All we need is the broad wavelength coverage to be able to not just measure, the thermal emission from the planet, but also simultaneously the region from the star itself. Okay, so we know that we need at least mid-infrared wavelengths to understand the planet's atmosphere and near IR wavelengths to understand the star's atmosphere. As Sasha touched on in his talk about life, mid-infrared wavelengths is a fantastic place to be searching for biosignatures. There are tons of molecules with great absorption features like methane, nitrous oxide, ozone, carbon dioxide, water, that when combined together and in sufficient abundances, can potentially suggest the presence of biosignatures. Now, there's a lot of debate around that, and we've had discussions about that earlier this morning, so I won't go into that. But it is an excellent place to be searching for life. Okay, so now let me introduce you to the observatory itself. This is a mid-X mission concept. It's a 2-meter aluminum mirror. 2 meters is but yay tall, right? But being aluminum, very easy to manufacture. We'd put the telescope at L2, similar to JWST, and of course we have to cool it down because we're looking at mid-IR wavelengths. We would use a broad wavelength spectrometer, somewhere in the region of 10 to 17 microns, simultaneous wavelength coverage, order R of 300. We would have an onboard reference calibration system, which is very important, I'll get into. And the idea is that we need to achieve a post-process precision of about 5 parts per million. Mission duration, 1 to 4 years, depending on funding and other such things. Okay, as far as the instrument is concerned, you might be thinking, well, JWST goes out to these wavelengths. Why can't that do it? Well, there are very specific improvements or enhancements to the instrumentation and the detector that would allow us to achieve that 5 part per million precision that JWST will not be able to achieve as far as I know at this point in time. First thing's the detectors. We are proposing to use Mercatel detectors similar to those used by JWST's near IR instruments, but pushing them out to longer wavelengths. The NEO survey is already commissioning detectors, Mercatel detectors, out to 10.5 microns. And the Rochester group has shown that they can actually push these out to about 17 microns. So this is a really compelling development technologically that allow us to achieve the level of precision that we're looking for. On top of that, there are new detector readout patterns being proven by Roman Space Telescope that'll help reduce the 1/f noise, this red noise that people have been talking about, showing in some of the light curves. And we also have an innovative calibration system that, within the use of an integrating sphere, will actually allow us to calibrate simultaneously while performing the observations, thus achieving the highest precision possible. Okay, so what are the science goals? First and foremost, we want to detect and characterize non-transiting rocky exoplanets orbiting the nearest M-dwarf stars. This will allow us to study both the host star atmospheres and the variability, and constrain planet radius, planet temperature, and or atmospheric composition of potentially habitable planets. Now, this is just an example phase curve of the hot Jupiter, but conceptually it would work the same way. Even if it's non-transiting, you see that you could actually measure the variation in flux of a non-transiting planet just by staring at over several orbits, right? And if you need to observe the system, I was talking about TRAPPIST-1e, where I was saying, hey, you need 85 transits to characterize this atmosphere, and they would take many, many years. The advantage here is that you don't need to wait 7 days or, in between 6 months to gather another transit. You can literally just stare at the system for 100 hours and keep gathering photons and then move on to the next system. So this is actually a very efficient means of studying exoplanet atmospheres because you're not relying on the transits or the eclipses to actually measure the thermal emission. So we have two different sort of strategies to characterize the atmosphere. The first one I'll talk about is just a simple science mission concept where we just want to measure thermal emission from as many high signal to noise targets as possible. And in this case, where you have an 18th-month program, 2-meter diameter mirror, the details are here. There are 37 planets that we could characterize just by measuring their thermal emission. And the distribution is shown here on the right. These are histograms showing planet temperature, planet mass, and K-band magnitude. And so we get a good distribution of habitable zone and exovenuses and exomercuries, range of masses, and so on and so forth. If, however, you wanted to do a slightly different type of observation where you wanted to measure the phase resolve, sort of a 4-quadrant phase curve, to be able to look for variability and infer presence of atmospheres that way, then we do a slightly smaller number of targets, 24 targets, where you're essentially mapping out the day side, the night side, and the quadrature emission from this planet. Now, the great thing about that, right, is that if a planet does not have an atmosphere, you're going to get a strong day-night contrast. So it'll be really clear with the phase curve whether or not it has a substantial atmosphere. Whereas, a planet like, the Earth or Venus, there's essentially zero measurable day-night contrast. So here's the distribution here. And again, planets in and out of the habitable zone. Okay, so let's try a case study here. What would we need to do to actually constrain the atmospheric composition of a potential habitable planet with the given amount of time, right? So for this case study, we looked at PROXEN-B, and this is a paper published last year by Avi Mandel. And we said, okay, let's give ourselves 100 hours of integration time with the 2-meter telescope. This is the level of precision that we'd expect to achieve on the planet to star flux ratio. And already you can see that we can resolve the large CO2 feature, but also ozone, and there might be methane and nitrous oxide in there as well. That's fantastic, right? And from that, we can run an atmospheric retrieval to be able to determine the abundance levels of these molecules and compare it to our inputs. And so this is something that Jake Lustig-Jaeger worked on for a while, and he produced the sort of tightly bound temperature constraints. You can see we're basically constraining the temperature very well near the surface. And because of the simple nature of the TP profile, we weren't actually fitting for an inversion, so it didn't show up in our tests. So we're doing a great job of understanding what the surface temperature is, which is key to understanding whether or not you can have liquid water there, right? That's an essential ingredient to life. If the temperature isn't suitable for liquid water, you have a much more harder time of detecting that life. And here I'm showing you posterior distributions on the abundances of given molecules, CO2, ozone, water, methane, and nitrous oxide. And again, we're getting tight constraints for each of these molecules just using this thermal emission measurements. This is 100 hours. This is less than the duration of this conference. We could have been staring at this planet and potentially detected biosignatures. That's how long it would take. And it's interesting, these black profiles here actually indicate the model inputs that went into it. It was actually a much more complicated model than we could fit for. And it was interesting to see that we were actually constraining mostly the abundances at the surface rather than higher up in the atmosphere. So that was actually a really interesting lesson that we had learned from this test here. Okay, so the next step, of course, is to reapply this with the JWST to see how well it would have performed. Obviously, it's a much larger mirror, so we shrunk the observing time down to 12.6 hours. So we've got the same level of precision, the same SNR, right? And so the purple posteriors are just the same ones from the last slide, and then we're adding in these kind of maroonish, reddish type posteriors from JWST case 8 here. And you can see just the difference in how we're able to constrain the molecular abundances of these species. CO2 can't be constrained at all. Water, not very well. Ozone, maybe an upper limit. And the thermal profile is significantly different over on the far right-hand side there. It's just not really well constrained with JWST. So a 2-meter class MIRECLE mission should be able to measure the radius, temperature, and atmospheric composition of this system with 100 hours, give or take. Okay, so there are several open questions that we're currently working on to address. First of all, how do you accurately fit the stellar flux? And second, how do you resolve multiple planets within the same system? So let's talk about the first question here. I will say right out, I don't have an answer for you yet. It is something that we are currently working on using JWST cycle 1 data. And this is a great example. This is a plot that I showed you back on Monday. I know that's a long time ago, but hopefully you remember. It's an M-dwarf system, GJ486, and we produced a calibrated spectrum using JWST, and then we fit models to it. And you can see, like the water absorption from the M-dwarf right here, right? I mean, that's very clear. We're doing an okay job fitting this spectrum. At the 30,000 foot level, we're matching, the broad stroked features of that. But when you zoom in on these panels below here, you see that we're not fitting every single bump and wiggle there that goes up and down. Some of them, yes, some of them, no. Do we need to actually fit every single one of them? No, as it turns out. But this is an ongoing process. And over the next 12 to 18 months, we'll be actively working on that. And we'll try to have more answers for you as to what resolution we want to fit, what wavelength coverage, and how well we're able to recover the spectrum. Okay, the next question, how do you resolve multiple planets in the same system? Well, for this, we're going to do a little case study of the TRAPPIST-1 system. This is work put together and led by Laura Mayorga, and you should expect to see that paper popping up on arXiv in the next few weeks or months once we go finish the review process. The idea here is that we want to be able to go through the discovery process of the TRAPPIST-1 system, started back in 2015 when we knew the star existed but didn't know any planets around there, and then stepping through, seeing how well the pi technique using MIRECLE would have performed in terms of detecting these planets and characterizing them as we gained more and more information through the various detection publications. And so on the right-hand side here, we have this familiar plot that you've seen before with the stellar spectrum, followed by planets B through H and their thermal emission that's been enhanced by a factor of 1,000,000, just so you can see. And it's a highly degenerate problem. If you look at it right now, just thinking about it, how are you going to measure the planet temperatures and radii of all of these planets in the system when they're so closely matched? It's not easy to do. So we set up our assumptions, simple black bodies, resolution, wavelength coverage, and then we fit for these three parameters right here. And if you have any questions about why we pick those, you can ask me later, or ask Laura. All right, I'd like to take a second to explain this plot here so that we can all get on the same page. This is showing the best fit system using the given number of planets in our assumption. So we know that the true system is down here, and here are the 7 planets that we're aware of that go into the model. And then we say, okay, now let's simulate it, assuming that we have 1 planet in the system. Would we detect that planet, and at what significance? Okay, so this is this row right here is our 1 planet case. And then we're actually giving a Bayesian evidence number and also a significance against the best fit model. So in this case, we detect 1 planet at this size, right? You can see that the symbol size represents radius and the color represents albedo. And when you say that there's only 1 planet in there, it basically combines B and C together and says it's about, it's larger, it's more like a super Earth, and it's, fairly hot. But as we add more planets in, it also detects that. So you can actually see based off the Bayesian evidence that it is preferring a 2-planet model over the 1-planet model. And it's doing a pretty decent job of constraining the radii and the temperatures. And of course, you can add more planets in and more planets in and more planets in, all the way up to as many planets as you want, right? Eventually, it becomes a degenerate problem where you've essentially added so many planets that it doesn't know where to put them and doesn't know what temperatures to have. But all you have to do is go back to the evidence and say, yes, back in 2015, before we knew there were any planets out there, had we used MIRECLE to stare at the TRAPPIST-1 system, we would have guessed that there are most likely 2 planets in the system, and here are their orbital periods and their sizes and their temperatures. That's not bad, right? If based off of just little bits of information, we can get a half decent constraint on these planet parameters. Now let's follow that up. Okay, let's go now to 2017, where Michael Guillon and his team have now discovered that using Spitzer data, that there's additional planets in the system, and then they constrain their semi-major axes and the radii. And we can go through that same process, and the best solution turns out to be really darn good, right? So that we are able to recover the planet sizes and their semi-major axes fairly well without too much information on the priors. And then again, also for Egal et al. 2021. Well, as it turns out, when we looked at this a little bit more closely, a lot of that information was prior dominated, right? It's really actually the semi-major axes and the stellar or the planet radii that was driving this method. And so we had to think carefully about what information we were actually getting out of this that was independent to MIRECLE. And as it turns out, it was temperature. Temperature was the piece of information that we could resolve that they were not getting. So this is in gray are the priors, and the posteriors are the colors. And then of course, the known values are those vertical dashed lines here. And so our 2015 model, where we had 2 planets, there were essentially very low priors on what the temperatures could be, but we actually constrained them to be fairly well. Of course, as the more planets were discovered, we were able to add them into the simulations. And you can see that based off of the priors, right, in gray, let's go down to the 2021 system, and the posteriors, we're actually constraining these parameters very well. So if we happen to know the radii of these planets, the temperatures are basically spot on. And so that was a really interesting lesson learned for this process. Okay, so MIRECLE can find previously unknown planets and constrain their sizes and temperatures, but it gets really difficult when you have a large number of planets in a tightly compact system like TRAPPIST-1. So it's good for solo cases or 2-planet cases, but maybe not so great for resolving TRAPPIST-1 system perfectly well. It can, however, constrain the temperatures, which is fantastic. All right, in my last 26 seconds and counting, I would like to highlight a project that we have worked on. Guangwei has worked on this project for the last day or day and a half. And basically we asked, can we actually test this pi technique using WAS43 phase curve data? And so what he did is he took little segments of data, right? The day side or versus the star only, or the night side versus the star only, and said, hey, if I just took that flux and did a ratio between the two of them, could actually pull out the day side and the night side thermal emission of the planet. As it turns out, yes, he could. As the most basic test, zero order test, he was able to pull out the thermal emission of the day side in blue and the night side in orange, and it matches actually pretty well to the phase curve observation that's been circulating in the ERS preprint. So the good news is, yes, the technique seems to work, and we're really excited about the next steps. So I will stop there because I'm out of time. And if you're interested in contributing to MIRECLE or anything pi related, please let me know. Thanks.
Hi, Kevin. Thank you for the great talk. I'm still trying to understand the pi technique a little bit better. So if it's non-transiting, are you getting the radius from the excess flux by measuring the color temperature of the spectrum? And if so, how degenerate does it become when you have atmospheric absorption and also kind of an albedo spectrum as well?
Right. Okay. So we can resolve the temperature planet radius degeneracy if you fully resolve the SED black body emission. In particular, you need the wean edge, the cool, the left edge of the black body to resolve that degeneracy. The peak of a black body changes as a function of temperature, right? And so if your precision is high enough, and your radius is just controls like the up and down, right? So it's essentially, it's not quite orthogonal, but it's pretty close. So if the planet radius is controlling the amplitude, and then the peak of the emission is controlled by the temperature, you can actually resolve those two given high enough precision. Right. If there's absorption features in there, it's a little bit more complicated. I invite you to look at Jake Lustig-Jaeger's 2021 paper, which went into that in detail. We are able to resolve the spectroscopic features. If you think about it from just a modeling standpoint, where you take a molecule like ozone or CO2 that's not going to be in the stellar atmosphere, you don't actually even need a absolute calibration on that. You can just look for ozone dips at 9.8 microns or CO2 dip at 15 microns and be pretty confident that it's not going to be coming from the star, and instead it's probably going to be coming from the planet, for example.
Yeah, so we have an online question asking, is a 5 parts per million noise floor realistic for MIRECLE or JWST?
Yes. I am optimistic.
Oh, hey, thank you for that great talk. I also have a question about the pi method. So isn't it extremely prone to any uncertainties on the stellar model that propagates through to the planetary spectrum? Because if you assign everything that you can explain with the model to the planet, then that sounds like it's going to be very dependent on the stellar model. Is that the case?
Yes, right. It highly depends on what your assumptions are for the stellar spectrum. And this is part of the test that we plan to do over the next 12 to 18 months on real JWST data. I mean, with Guangwei's test, he was using the in eclipse data as our stellar model, which is perfect, right? This is a perfect representation of the star. But when you move away from that, when it's not transiting, or if it doesn't have an eclipse, you now have to depend on models, which you're absolutely right, is going to be a challenge, and I think is the biggest hurdle at this point. I'd love to stand here and tell you it's not an issue, but I honestly don't know. So we'll find out.
Thank you.